The cryosphere is the ice mass of our planet, the ice sheets, permafrost and water ice of the poles. A moderator of ocean and atmospheric temperatures, a sun reflector, the cryosphere is an integral part of this planet's cooling system. Climate change is shrinking the ice caps, and it's a runaway effect. Our world is warming, the oceans are rising, and we need to do something about it. Of all the fresh water on Earth, 99% is stored in ice sheets, the large frozen masses that form over land. As climate changes, melting ice sheets can contribute to rising sea levels, which can place vulnerable cities around the world in jeopardy. From the South Pole to Greenland, from Alaska's glaciers to Svalbard, NASA's Operation Icebridge covered the icy regions of our planet in 2017 with a record 7 separate field campaigns. The mission of Icebridge, NASA's longest-running airborne science program monitoring polar ice, is to collect data on changing ice sheets, glaciers, and sea ice, and maintain continuity of measurements between IceSat satellite missions. World-renowned leading climate scientist and astronaut Dr. Piers Sellers was director of the Earth Science Division at NASA Goddard. Having seen Earth from space on 3 shuttle flights and 6 EV-8, Dr. Sellers was deeply concerned for the future of our climate.
Icebridge is probably one of the most important field campaigns we have running right now. The world is warming, and it's warming faster in the north, around the Arctic, than anywhere else by a factor of 2.5. It's 2.5 times increase in warming here compared to the global average. So this is where it's all happening. And as a consequence, the ice is melting fast. It's melting on the Arctic Ocean, and the ice mass on top of Greenland is melting and falling into the Atlantic. So we're mapping that using aircraft and satellites where we can. And of course, we've got people on the ground checking against these data as well. So this is ground zero for global warming. We're doing a lot of work here, we put a lot of effort into it, and I think it's paying off in terms of improved understanding.
Operation Icebridge began in 2009 and continues to fly aircraft through the region with advanced sensing equipment and coordinated land traverses by scientists to ensure accuracy of satellite data. Now, in conjunction with the European Space Agency, they coordinate and share data with additional satellite assets which fly identical science instruments. Just why are the ice caps melting? Because of the so-called greenhouse gases, carbon dioxide, methane, nitrous oxide, and fluorinated gases in the atmosphere. Together, they heat up the atmosphere by trapping energy. While CO2 has always been part of the atmospheric makeup, it has changed since the Industrial Revolution.
In the pre-industrial age, the CO2 response to temperature was that the temperature would go up and CO2 would go up. Or if the temperature went down, CO2 would go down. And the reason for that is when the temperature went up, the whole biosphere revved up and emitted CO2, and we had more CO2 in the atmosphere. So we understand that process. The problem for the science community is in the post-industrial age, the CO2 rises preceding the temperature rise. So two different things happened. One pre-industrial, where temperature was driving the CO2. Post-industrial, where the CO2 is driving temperature, which means a completely different physical, biological process is going on. And we don't understand what the consequence of that change is. It is a fundamental change to how the Earth works and how the Earth's radiation balance works. And so, since we don't understand it, we're very concerned because we don't see any restraining force on continued increase in temperature due to continued increase in CO2. And that's a problem.
Warmth tipped the scales again with the hottest October on record, but also the fourth hottest year to date for the globe, according to a fresh analysis by scientists at NOAA's National Center for Environmental Information. Generating long-term data sets is extremely important when studying climate, so to maintain continuity, a new generation of Earth observation satellites are coming online. ESA have deployed Aeolus, METOP-3, Sentinel-C, and NASA have launched ICESat-2, the JSSC, and the follow-on GRACE missions. All of these satellites have one instrument in common that measures altitude.
A radar altimeter is a beautiful instrument because it measures almost everything we need on the planet. It measures the height of the sea, the height of the ice caps, but also we can use it to measure the heights of lakes and rivers, even derive river discharge.
METOP-C, the third in the METOP program, carries no fewer than 13 observational instruments. Some are identical to NOAA's suite of satellites.
We have 10 instruments on board METOP. It was a very large platform. And these instruments are also provided by different organizations. We have a set of instruments provided by NOAA NASA. We have instruments provided by CNES. We have instruments which are procured by ESA, and some other instruments which are procured by EUMETSAT directly.
So METOP-C is the last satellite of a cooperation program that we have with the NOAA in the United States as part of what we call the initial joint polar system. So in 1998, EUMETSAT and NOAA signed this cooperation agreement where three European satellites, so three METOP satellites, were corresponding to three US satellites. And for these satellites, we share instruments so that the users get information from both satellites, the same types of information. So we try to create synergies between US and Europe, more benefits to our user.
We didn't expect we'd be able to measure sea level to just a few millimeters every 10 days. And having such accurate measurements for 25 years has let us monitor sea level rise and even perhaps detect an acceleration in the sea level record. And that was something that wasn't envisioned 25 years ago. But as the technology has gotten more and more accurate, we've been able to make more and more accurate measurements of sea level. And so we can be even more confident in our results. Combined with, we have other observing systems other than altimetry. We have a gravity mission called GRACE, where every month we weigh the ocean. And we have robots that float throughout the sea, about 3,000 to 4,000, to take the temperature of the ocean every few days. So when we add up the results we get from the gravity mission where we weigh, and where the Argo floats where we take the temperature, we get almost exactly the same answer that we get from the radar altimeters, to within a few millimeters. So we're very confident in our results that we're seeing 25 years of sea level rise of about 3 millimeters per year, which doesn't sound like a lot, but as we see it starting to increase year after year, we know that acceleration will be very devastating for coastal communities all over the world.
Aeolus, ESA's newest Earth Explorer satellite with which the agency will measure wind profiles from space with laser technology.
At the moment, we have a very poor understanding of how the wind is around the globe, and we need more knowledge about that. But that's the information you need to start. You need to have a picture of how is the weather now to be able to predict how the weather is in the future.
Aeolus is a relatively short mission to demonstrate the potential of the Doppler wind LiDAR in space. And once we can demonstrate that actually it's made a decent impact on the numerical weather prediction forecast, then hopefully we can have an operational follow-on mission, or maybe several satellites in tandem rather than just one satellite. It's not just wind information, actually. You need to also know temperature information, pressure, and humidity information. But the winds are a key component of that information that you need to know right now to work out the weather in the future.
Sentinel-3A was launched in 2016 and 3B in 2018. Both satellites primarily focus on our oceans. They measure the temperature, color, and height of the sea surface, as well as sea ice thickness. These measurements are needed to study changes in sea level, marine pollution, and biological productivity. Sentinel-3A has already yielded interesting results.
The Sentinel-3 mission is actually quite a versatile mission in the sense that it serves a large variety of different Copernicus services. So we're not just working with the Marine Environment Service, we're also working with the land, with the atmosphere, and with the climate service. There's a large variety of data that we can actually supply. The Marine Service is probably the most developed for the moment. It's already using data over the ocean, in particular the ocean color data, which tells us something about the marine ecosystem, about the health of the sea, and can basically also predict something like harmful algal blooms. Snow cover gives us an idea about the snow water extent. So basically that gives us an idea of when this melts, for example, where we go in terms of flood forecasting, runoff models, so for hydrological applications, but also for weather forecasting, for example.
Sentinel-3 mission is supposed to last until 2040 at least. So A and now B will be in space soon. The C and D model, which are replica of this one, are under manufacturing now and will be completed by the end of the decade. And they are expected to be launched in the 2023-24 time frame to cover basically the Sentinel-3 mission until 2030.
That's why we want to have continuous measurements. So we have planned with the next series of JASON missions, JASON CS or Sentinel-6, that we'll have at least 10 more years of measurements because we need to keep monitoring the sea level as it accelerates.
With this long-range forecasting, the acceleration of global warming can be monitored and better predictive models developed.
Yes, that's why by having all three measurements, that helps us understand the cause, that we can see from GRACE a measure of which continents the water is coming from, that Greenland and Antarctica are melting, and some glaciers are also melting, and we can also see as the temperature of the globe increases, we can watch the water in the ocean actually expand from more and more heat.
Scientists on the ground continue to innovate ways to improve satellite data accuracy. Surfing for science may seem far-fetched, yet that is exactly how Dr. Bob Bruin of the Plymouth Marine Laboratory is pioneering a new technique in satellite oceanography. By equipping his surfboard with a device called a smart fin, Bob can measure sea surface temperature and motion of coastal waters with his smartphone. Later, Bob can use the smart fin data he has gathered to better interpret Sentinel-3 satellite data. The Sentinels are part of the Copernicus program. Using the three instruments on board, the satellites gather information on ocean color, water quality, changes in sea level, and, most important for Bob's research, sea surface temperature.
With over 40 years of thermal radiometry we have now from our satellite platforms, we can begin to get a really good understanding of how temperature is changing in the nearshore environment. And temperature is a critical component of our oceans. It controls the biology through changes in growth rates and reproduction. It controls the physical environment together with salinity. It controls the density of the ocean, how coastal currents move, and it's also a fundamental component of marine chemistry. The reaction rates of many chemicals are temperature dependent. The gases that move from the atmosphere to the ocean are temperature dependent.
In situ data gathered by scientists like Bob is extremely important as it complements and helps to verify data provided by the Sentinel satellites. For example, the temperature of coastal waters is difficult to measure from space, though they have very high levels of marine biodiversity. So scientists find new and ingenious ways of increasing the number of in situ measurements in these waters. With the SmartFin, for instance, surfers and other water sport enthusiasts can gather data while enjoying their hobby. Meanwhile, NASA has dispatched 2 new satellite missions to observe the most critically changing regions, the poles. NASA and the German Research Center for Geosciences, GFZ, has launched GRACE-FO, continuing the revolutionary gravitary measurements of its predecessor, GRACE. ICET-2, with an advanced laser altimeter system, is continuing the work of its predecessor. This new technology will help study ice sheets, but also sea ice, glaciers, permafrost, and snow cover. Collectively known as the Cryosphere, these frozen zones help sustain stable conditions for life on Earth.
ICET-2 is NASA's latest technology to measure the elevation or the height of ice sheets, and by repeating those measurements through time, we can measure how ice sheets are changing. It'll also allow us to measure the height of sea ice, which is a way to understand the thickness of that sea ice. And so it's really a huge advance forward in both our precision of elevation change measurements as well as coverage. Each of those 6 beams gives us much more data than we've ever had before. ICET-2 is designed and built here at NASA's Goddard Space Flight Center, and it does take advantage of many of the latest advances in that technology. It's really an excellent tool for studying changes in ice sheets and in sea ice. For sea ice, it's really critical. It plays a first-order effect in weather patterns around the world. Sea ice in the Arctic Ocean regulates the exchange of heat and water vapor between the ocean and the atmosphere. And as sea ice gets thinner or thicker, it either allows more or less of that heat exchange to happen. For ice sheets, as that ice is lost back to the ocean, it directly goes into sea level rise, which of course impacts folks worldwide.
So NASA scientists crossed the Antarctic, taking altitude and radar depth measurements to help calibrate ICET-2's instruments.
One of the other experiments we were doing is leaving out what we call corner cube reflectors to get an assessment of the pointing of ICET-2. When we make an elevation measurement, how are we sure it's in the right place? So in this picture, you can see a bamboo pole with a little white cap on the end of it. And embedded in that cap, a little piece of glass about as big as your pinky nail, and calibrated to return green laser light from the satellite.
With the requisite observation tools in place, the next step is to interpret the data.
Ice sheets are actually really dynamic, and they flow under their own weight from the center of the ice sheet out to the perimeter of the continent. In the really cold regions and way high up on our ice sheets, we get a lot of snow accumulation, and over time, that accumulation can build up. If it stays cold enough and that snow persists, and then you get another year of snow and another year of snow, you can imagine the weight of the snow on top of itself forces some of the lower layers to compact. We call that the firm densification, the top layer of the ice sheet. When we talk about the health of our ice sheets, we talk about the mass balance of the ice sheet. Basically, that means coming in is in balance with all the terms of water or ice going out.
The health of the ice sheets depends on a balance of these terms of input and output, but the interaction of the atmosphere, ocean currents, and temperatures can force the ice sheets out of this equilibrium.
At a big scale, the winds in Antarctica are kind of spinning in a big clockwise direction around the continent. But you can imagine a big dome of ice has very little obstruction, like trees or mountains kind of steering the winds. Consequently, winds that sort of are gravity-driven and come down the continent can build up speed really quickly and again uninterrupted by any sort of disturbance. And we call those katabatic winds. And they have a major influence on what happens at the edge of the continent. Around Antarctica, there's a massive current that we call the Antarctic Circumpolar Current, and it flows clockwise around the continent. Close to the continent, we also have the Antarctic Coastal Current, stays really close to the coastline and flows counterclockwise around the continent. In addition to these continent-scale currents, we also have regional-scale currents, such as gyres. Gyres are these parts of the oceans that are sort of isolated because of topography or ocean bottom topography. They're usually closed currents that often circulate. The gyres have a big role in sea ice formation and also in the currents that actually flow underneath our ice shelves. You can imagine that around the edge of the continent, near those ice shelves, warm water from the ocean can intrude into that cavity and contribute to basal melting, the melting from warm ocean waters up at the bottoms of our ice shelves. Calving in Antarctica is a little bit sporadic and it's hard to actually model, but some of the contributing factors associated with calving include those strong katabatic winds pushing on the edge of the ice sheet, pushing on the edge of the ice shelf, and calving large icebergs. So we're measuring surface elevation, and we can take that vertical measurement, kind of integrate it over the whole ice sheet and get a volume change. And then the real science of ICESat 2 is taking that volume change and turning it into a mass change. And from that, we can determine how much ice is actually turning into water in our oceans and raising sea levels. So the Greenland ice sheet is thinning, and it's thinning variably, but mostly along the coastlines. It's thinning beyond our expectations. And all of that thinning is taking place upstream of where the ice sheet is grounded. Therefore, that is going right into the ocean and contributing to mean sea level rise.
Since we launched ERS-1 in 1992, we have been working on the radar altimeter time series, and we have derived a 25-year-long time series of sea level rise. Sea level rise is a major indicator of climate change because it integrates, for instance, the melt of Greenland and Antarctica. We have analyzed this series and we have analyzed the error, which is under control, and so the scientists are convinced that now we have clearly on average 8 centimeters of sea level rise, but we also have regional variation. For instance, in the tropics, it's 3 times that value. And what we have also analyzed with the recent data is that in the last 5 years, sea level has been accelerating. So it's not 3 millimeters per year or 3.2 millimeters per year. It's more like 5 millimeters per year. We have provided this data to people doing projections, to scientists, climate change scientists doing projections, and they have modeled the sea level in 2100, which is expected to be 2 meters higher than today.
This animation shows how different the globe will look by then, and prompts us to consider where the food and fresh water will come from.